Welcome to the course on VLSI physical design with timing analysis. In this lecture, we will discuss about timing arcs and unateness. So, the content of this lecture includes definition of the timing arcs, then we will discuss about the what is source pin and a sink pin in a timing arc. Then there are different types of unateness like positive unnate, negative unnate and non-unnate types of gates, and what is the use of unateness in any kind of digital circuits and how it is used for timing analysis. So, first of all we will discuss about the timing arc. So, what is this timing arc? So, it is basically defined as the it is defined as the relationship between two pins of a logic gate. It can be, this logic gate can be a combinational or a sequential. So, this timing arc is also useful, it is useful for the STA tool to do timing analysis. And we have different types of timing arc. So, it is divided into two parts. So, it is basically a part of the timing path. It is divided into basically two category, two types. One is called your cell arc and the second one is called the net arc. Okay, so we will discuss what is a cell arc and a net arc with an example. Okay, so let us say I have a path. Here if you can see, let us say it is a NOR gate, then we have a AND gate, then a buffer. So, it is a mixture of gates are there. Then again you have a XOR gate like this. So, which one is your cell arc and which one is your net arc? So, these gates we can use different color. This logic gates are basically your cell arc. So, because these cell or logic gates are part of the timing path and these are called the cell arcs, and we have net means interconnect or a wire. So, these I can draw it in a different color. So, these are my net arc. Okay. So, we need to consider both the cell arcs and the net arcs in the timing path. So, this is a timing path from input to the output we have a timing path. So, it consists of some cell arc and some net arc. Okay. So, this is the basic of your timing arc. Okay. Now, we will go into what is source pin and the sink pin. And sink pin. Okay. So, if you can see here one example I will show you, then I will explain what is source pin and sink pin. Let us say I have a gate here, this is a NOR gate followed by a NAND gate, or you take a AND gate. Okay. So, let us say this is A pin, this is B pin, this is C pin. Okay. This is let us say the gate 1, this is gate 2, okay. And this is your output. There are two outputs, let us say we can, this is O1, this is O2. Okay. So, here if I can see you your basically your gates. So, what are the source pin for gate G1? Your B and C are the source pin, and for and your O2 is the sink pin. Okay. So, source then the sink. Okay. Now, for gate 2, your basically A and O2 are the source pin, and O1 is the sink pin. Okay. So, this is the concept of source pin and sink pin. So, now we will discuss a few more examples. In case of a I will generalize few things. In case of cell arcs, okay. Okay. So, in case of cell arcs, your input pins, the input pins are source pin, and output pins are sink pin. But in case of a net arc, in case of net arcs, the output pin of the so input pins of the cell, input pins of cell, here input pins of cell, output pins of cell. So, here basically output pin of the cell, output pin of cell are source pin, and input pin of the cells are sink pin. Okay. For example, if you can see here this is a net arc. Okay. This is a net arc. So, the output pin is the, so this is a net arc and the output pin is your source pin and the input pin is just sync pin. This is the input. So, this is a sync pin and this is the source pin for the net arc. This is the source pin for net arc. This is the sync pin for net arc. Similarly, these are your source pin for the cell arc. These are the source pin of these are the source pin of cell arc and this is the sync pin of the cell arc. Okay. So, this is the concept behind the source pin and the sync pin. Now, we will go into the details about unateness. What is unateness? Okay. What is unateness? So, this unateness is one of the important parameter for timing analysis and it is used by the STA tool and we will explain this with some analysis. So, basically each timing arc has a timing sense actually, each timing arc has a timing sense. So, each timing arcs has a timing sense. What is the timing sense is that it is denoted by unateness. So, what is this timing sense is that what it says that change in the output transition with respect to input transition, that is called timing sense. So, this is used in case of static timing analysis. So, if you know how your input and output transitions are related, then the timing analysis tool will pick the right delay value from the dot leaves. We will discuss that in detail. So, now we have three types of unateness. One is called positive unat. What is this positive unat? So, if your input signal is rising, then your output signal is also rising, is rising or no change. Or you can say the input signal is falling and your output signal is falling or no change. Okay. So, we will discuss this one with one example. Let us say take a case of a buffer. So, we have a buffer. I have this this is the buffer. So, how many timing arc is there? you have seen here, if your input is rising here, okay, output will also do a rise transition in case of a buffer. So, I have this is one arc. So, if this is first arc, this is the second arc. If your input is falling, if your input is falling, then your output is also fall after a certain delay. Okay. So, this is your this is, that is why it is called positive on it. So, input is rising, output is rising, input is falling, output is falling. So, let us take a case of a AND gate. Let us second example, AND gate. It is interesting. Why? Because it has multiple timing arcs. Okay, it has multiple timing arcs. For example, I have a AND gate. Okay. It has two pin A and B. It is 2 input AND gate, and your Y is your output. So, let us say your B is 1, B is fixed at 1. So, input is rising, then your output will also rise. So, this is one arc. Okay. So, this is one arc. Then the second one is, let us say my input is falling, B equal to 1, my output will fall. So, this is the second arc. Then the third arc is basically I have let us say A equal to 1 and B is rising, your output will also rise. Then the fourth arc is A is 1, my input is falling, my output will also fall. This is the fourth arc. So, all the cases your input is rising, output is rising, input is falling, output is falling. So, then there is another, these 4 arc is actually used, and there is another arc is also there, but it is not used. We will explain why it is not used. Let us say one of the input is 0, let us say B is 0. Okay. So, if I do a rise transition here, your output will not change. Okay. So, here there was a condition that either rising or no change, output is not changed, but it is not a arc. Why it is not a arc? Because if I put this gate with B equal to 0 in a path, then the signal will not propagate from input to the output in that path. So, it will stop there, it will stop there, the signal will stop there. That is why this is not a arc. So, your AND gate has 4 timing arc. Similarly, you can do it for A equal to 0 also, those are not arc, because your signal will not further proceed in the path. So, your AND gate has 4 timing arc. Now, we discuss about the positive on it. Now, we will discuss about the negative on it. So, what is negative on it is that here the opposite. So, what is the opposite? is that, let us say your input signal is rising, okay. So, your output signal is falling or no change, your output signal is falling or no change. Okay. Similarly, you can say input signal is input signal is falling, means that output signal is rising or no change. Okay. So, here, so let us say take an example of a inverter, one example I will take inverter which is having two arc. Let the first arc is, let us say I have a inverter here, let us say I will do a rise transition in the input, output will fall. So, this is a arc, timing arc. Similarly, the inverter it will fall, then output will rise. Okay. So, inverter is negative on it because input is rising, then the output is falling, and input is falling, then the output is rising, and it has two timing arc. It has two timing arc for a inverter. Now, take an example of a NAND gate. Okay. Let us do it in the next slide. So, 2 input NAND gate. So, what is happening? Let us say I have a NAND gate is there, I have a NAND gate is there. If my B input is 1, okay, if my B input is 1, my, let us say my other input is rising, okay, other input is rising, your output y, let us, this is A, output y will fall. Okay. Similarly, if I have another case B equal to 1 and my input A is falling, this is the, then your y will do a rise transition. So, this is the second arc. Similarly, let us say your A is 1 and B is doing a, the B pin is doing a rise transition, your output will do a fall transition. Your A is 1 and B is doing a fall transition, then your output Y will do a rise transition. Okay. So, these are the valid arcs. Okay. You have 4 arcs, but there is a arc is there which is not valid, because let us say if I do a NAND gate, okay, if I do one of the input, let us say your B is 0 and A is doing a rise transition or fall transition together, let us say I am doing rise and fall transition. Okay. Your A is doing a rise and fall transition. Your Y is basically A B bar. So, B is 0 means A into 0 bar. So, 0 bar is 1. So, output will be held to VDD irrespective of change in the A input. So, even if you do transition in the A input, the signal will not pass to the next stage. So, it is not a valid arc, timing arc. So, your 2 input NAND gate has 4 timing arc. So, now we discuss about the positive on it and negative on it. Now, we will discuss about the non-on-net gate. So, non-on-net gate is such a gate, it your output transition, output rise and fall transition will not basically directly reflected on the input rise and fall transition. It depends upon the what is the condition in the other pin. We will discuss this with one example. So, let us say you have a XOR gate. Okay. So, what is the table of a XOR gate? So, you have A, B and Y, both the inputs are same, your output is 0 and 0 1 1 1 0 1 1 1 0. Okay. So, this is a XOR gate. So, let us say you have a XOR gate, okay, this is a XOR gate. Okay. So, let us say my A is 0, okay. A is 0, okay. Then B is doing a transition from 0 to 1, B pin is doing a transition from 0 to 1. What will happen to my Y pin? What will happen to my Y pin? So, initially B is 0, A is 0, output is 0, okay. And when B is changing from 0 to 1, so it will go to 1, you will get rise transition. So, your input and output is behaving like a positive on it, behaving like a positive on it. If my A equal to 0, let us say I have another case, I have XOR gate, this is your Y, this is A equal to 1 and B is doing a rise transition, okay, B is doing a rise transition. So, let us say your A is 1, A is 1 here and B is initially 0. So, your output will be 1. So, now B is changing from 0 to 1. So, now A is 1, B is 1, A is 1 and B is 1. So, your output will change from 1 to 0, output do a change from 1 to 0. Okay. So, here what is happening that it is a negative on it, if my A input is 1. Okay. So, XOR gate is a non-on-net type of gate. Okay. XOR gate is a non-on-net type of gate because your output transition will depend upon the state of the other input, whether A is 0 or 1. So, based on that you cannot tell that a positive on it or you cannot tell that a negative on it. When you do this gate timing analysis in a path, we have to know what is the condition in the other pin, what is the condition of A pin or the B pin in case of transition happening in the A pin. So, this is an example of non-ONET gate. So, this is a dot leaf which is used for timing analysis. So, if you can see here, this is timing sense, whatever I was talking about, how my output transition depends upon input transition. So, is defined here the timing sense, which is a negative on it. Negative on it means that whenever you do a rise transition at the input, output will do a fall transition and vice versa. So, this is a gate inverter, basically this is a inverter. So, here if you can see, it has mentioned that for a inverter the timing sense is negative minute. So, this is used in a timing analysis tool. The timing analysis tool will check that it is a negative on it, and based on that it will do the timing analysis. Based on that it will do the timing analysis. So, this is one of the use of basically negative on it. So, we discussed about the timing arc of combinational circuits. What about the sequential circuits? So, the timing arcs of sequential circuit. Okay. So, let us take an sequential circuit. This is a D flip flop. So, you have a clock pin. So, this is a clock, this is a D pin or data pin, then you have a Q, then you some of the D flip flop has Q bar, and you have asynchronous reset. Okay. So, if you can see here, it has many timing arc. So, for synchronous input, okay. So, in case of synchronous input, you have basically setup arc, setup check arc. Okay. So, it has two variety, rising and falling. Okay. Now, we have hold arc, hold check arc, rising and falling. Then these are for the synchronous input. Okay. So, similarly, you have asynchronous input, basically your clock for synchronous input, your clock to D. Okay. You have setup check and the hold check. So, these are the arcs for setup check arc from the clock pin to the D pin. Similarly, for asynchronous input, okay, for asynchronous input, what is the asynchronous input here? Your reset pin is a asynchronous input. So, here we have two types of arc is there, recovery check arc, recovery check arc. The second one is removal check arc. Okay. Now, you have third arc is there, which is called for the synchronous output. Okay. So, what are the synchronous output? Your Q and Q bar are the synchronous output. So, for that one you have one arc is there called clock to Q, clock to output, propagation delay. Okay. So, that is also have rising and falling. Okay. So, these are the arcs basically involved in case of a sequential circuits. These are the arcs used in case of a sequential circuits. First of all, we will discuss about what is setup arc and hold arc. So, we have a flip flop and we have basically we have a flip flop, it has a clock signal and it has a D pin and a Q pin. Okay. So, now we can have basically first we will plot the clock signal. This is your clock. Then you have a data D which is coming before the rising edge of the clock, which is coming before the rising edge of the clock. Let us say it is going like this. Okay. So, what is the minimum time before the rising edge of the clock? Your data should be stable, that will be sampled by the clock properly, that is your setup time. Okay. So, we are checking before the rising edge of the clock. So, this is your setup time. Similarly, after the rising edge of the clock, what is the minimum time I can keep the data stable such that it can be captured by the clock properly, that is your hold time. So, this corresponds to setup arc and this corresponds to hold arc. Okay. So, these two is very essential for checking the timing. Now, we have one more component which is also with respect to synchronous output, okay, which is basically clock to Q propagation delay. If your setup hold constraints are met properly, you have a Q signal, this Q, which is the output of the flip flop. So, let us say this is your clock signal, your data may be anything before the rising edge of the clock, but since the data is satisfying your setup and hold requirement, it will come after some time after the rising edge of the clock. So, then this will be available at the output of the flip flop. So, this is basically your this distance is basically your clock to Q delay, T clock to Q delay, and this is basically clock to Q delay. Now, we have one more arc is there which is related to the asynchronous input reset. We will discuss that in detail. So, what is a reset? Reset is a signal if you apply to the flip flop, the output of the flip flop will be 0. So, I have a flip flop, this is clock, this is a D pin, this is Q, okay, and we have a another signal, let us say here reset. Okay. So, in this case reset is active high. Reset is active high means that when reset is 1 means that your Q becomes 0 irrespective of the whatever the data D applied to the flip flop. So, what is the situation here? If I have any clock here, let us say this is clock. Okay. Now, I have a basically D input. Okay. D input is changing like this. Then I have a reset. I can apply the reset anywhere. Let us say it is active high. Okay. This is active high here. Okay. So, now let us say I will apply here again. So, what is the point here is that, so here we are assuming that our reset is active high. So, here it is going from 0 to 1. So, it is called assertion. This process is called assertion, and when it is going from 1 to 0 is called deassertion. So, here what is happening is that we have applied a reset and we have D input is there, we have a reset is given to us, then which will be basically driving the Q output. So, here the reset is applied or asserted. So, your Q will be 0 after some time. So, here the Q can be anything before that, okay. It can be anything before that, but after the reset is appearing. So, it will move from whatever the states to 0 state once the reset is applied. Okay. Now, again here it is again it will go to 0. So, this is the basically the meaning of assertion and deassertion. Assertion means that we are changing the reset from 0 to 1, deassertion means that we are changing the reset from 1 to 0, okay, where we are assuming that our reset is active high. Now, with this background we are going to discuss what is recovery check arc and removal check arc. Recovery check arc. Okay. First, we will discuss the recovery check arc. In case of recovery check arc, we are basically deasserting the reset signal, and then we are giving control to the flip flop, and flip flop should be driven by the D input instead of the reset input. And one more thing is that what is the minimum time, okay, what is the minimum time required between the deassertion of the reset signal and the arrival of the clock signal, such that the new data can be captured by the flop, that is called your recovery time. Okay. So, what is the situation here? I have a clock signal, this is my clock, and I have a reset signal. So, it is active high, okay. So, it is active high. So, it is changing here. So, then we have a data input D which is changing here. Okay. Now, we have a Q which is the output of the flip flop. So, what is this minimum time before the rising edge of the clock? Reset should be deasserted. So, what is the recovery check arc is that what is the minimum time, this time before the rising edge of the clock, your reset signal should be deactivated or deasserted, such that your new data D can be captured by the flip flop in this edge. So, that is your recovery time. So, in this rising edge your new data can be captured. It will take some delay and it will appear at the output. So, this time is your recovery time. This time is your recovery time. Okay. So, this is all about recovery check arc. Now, we will discuss about the removal check arc. So, here we have a clock edge. We are drawing the clock first. This is clock. So, now I am drawing the reset signal. So, the reset is deasserted after the rising edge of the clock, and whenever you are deasserting the reset, how much minimum time after the rising edge of the clock it should be deasserted, the output will be 0, output will be 0. What is the minimum time my reset should be deasserted after the rising edge of the clock such that my Q should be 0. So, here if I have a data, if I have a data like this, then my Q will be changing and capturing the data in the next clock edge. In the next clock edge. So, this time is called my removal time. So, in summary, this is the minimum time after the rising edge of the clock, the reset signal should be deasserted such that my Q is 0, and it will act as a normal flip flop in the next rising edge. So, basically here why you are giving this minimum time here is that basically your Q output is driven by two inputs, one is the reset input and the D input. So, there is a chance that both the things can create a metastability inside the flip flop. To avoid that, we need some amount of minimum time after the rising edge of the clock, your reset signal should be stable such that your output will be reset, Q should be 0. So, this is all about removal check arc. So, if you look into this dot lib or the timing library, this is the setup rising, timing type is setup rising, and this was the table for that one. So, this is giving an example of a setup rising arc in case of a sequential circuit. So, how this tool requires this information to do the timing analysis in the complete path was stated here. So, the unateness and timing arcs are essential for the timing analysis of any digital circuits. So, in this lecture we discussed about unateness, source pin and sink pin, and different types of unateness like positive unet, negative unet and non-unet types of gates, and we also discussed about the timing arcs of the sequential circuits. So, this is very useful for timing analysis of digital circuits. Thank you for your attention.